morning. Welcome to Unit 3 of Dynamics. We finished kinematics where we described motion. And that's really what kinematics is all about, describing motion. Today we're going to be looking at dynamics, which involves motion as well, but in just a different way. It's going to be what causes the motion. So that's the difference right there. Dynamics is really what causes motion, while kinematics, which we just finished looking at, describes the motion. So when we had the different objects moving up a hill, down a hill, ball getting thrown in the air, how long does it take to get to the top, how high is it when it's actually at the top, how long is it in the air in total, all describing motion within kinematics. With dynamics, what we're going to be doing is what actually causes that motion to begin with. So for that ball to be tossed into the air, how much force would be needed in order for it to be traveling at an initial velocity of like 12 meters per second? Or if you were to pull somebody off of a merry-go-round, with how much force would you need to pull an individual off? If you're accounting for the force of friction based on what they're standing on, the mass of the individual that you're trying to pull, all comes into mind when looking at the dynamics of a situation. What causes the motion? You would have to look at all the forces involved within that. Now, below what we have is what's called the fundamental forces. This is just more purely for interest's sake. There's a variety of different types, and for the most part, we're only going to be focusing in on one of them, and we might as well start off with that one. So the force of gravity. And if we want, we can list all the four fundamental forces right now. There's all kinds of forces that fall into specifically the electromagnetic force category. But there are a total of four fundamental forces. Electromagnetic force, the strong nuclear force, and the weak nuclear force. Each of them has relative strengths as well as ranges in which they affect objects. Now, the force of gravity is actually the weakest of all of these different forces. So you may never have actually even heard of some of these before. Maybe you have. Strong nuclear, weak nuclear, or the electromagnetic force. Within electromagnetic force, you're talking about like frictional forces, tension, applied force, like when you like push on an object. I have a calculator here. I'm applying a force to move it forwards. That would be considered an electromagnetic force. Anyways, back to force of gravity. What we have here is essentially an attractive force between two objects with mass. Normally, we talk a little bit about the force of gravity due to the interaction with us and Earth. There is all kinds of gravitational forces. It's not just between the Earth. So like we will experience, yes, a gravitational force of 9.8 meters per second squared towards the Earth. But the Earth is going to be experiencing a gravitational pull towards the sun, and that's what actually keeps it in its orbit. You have the moon, which has a gravitational force being pulled towards the Earth, and the Earth is pulling it towards the moon, and vice versa. And it actually is every single object in the entire universe has some specific type of gravitational force. So even this pen right over here has a gravitational force. And so currently, right now, this pen is attracting this calculator, and this calculator is attracting this pen to it. But due to the size, its mass, which is very, very light, and especially in comparison to the mass of the Earth, the forces that are interacting between these two is essentially negligible or zero. And that's the general consensus here. So if you did actually do the calculations here of what kind of force is this calculator attracting to this pen or the pen to the calculator, you're going to get such a small value that it's essentially zero. And that's where you can get the joke where you can say, well, the larger you are as an individual, the more attractive you are, because the more mass you have, the more attractive you are to not only other people, but to other objects. So this one here, it's the weakest force of them all. And if we're talking about kind of like relative strength, this is more purely for interest's sake. It has kind of like a value of 10 to the negative 38 in comparison to if you were to say that the strong nuclear force had a value of 1, which this one is the strongest of all the forces, which is nice, easy to tell. It's got it in the title right over there, strong nuclear force. So it has the weakest force and the relative strength of it, but it also at the same time has the largest range. Well, it's tied for the largest range, which is an infinite amount. So this is the infinity sign right over here, an infinite amount of range. So you can continue traveling further and further and further, and this pen will still actually have a gravitational force and pull on it with every other object in the universe. But again, its mass is so incredibly light that the amount of gravitational pull that it has on any other object is going to be essentially zero. But take the sun. The sun is going to be affecting many, 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 many things. All the planets in our solar system, for example, and many other things beyond that too, where there's going to be a pull towards the sun. And that's where you have some of these orbits coming from. The fact that you're going to have this gravitational pull. And then there's all the stars beyond that as well. So that's the force of gravity. It's going to extend its range to an infinite amount. With your electromagnetic force, this is where you see things like this. Like charges repel. So if you have like 2 protons over here, they will repel. You have 2 electrons, they will repel. This is something that is not new at all. Similarly, opposites attract, right? So you have 1 proton, 1 electron, they will attract to each other. Other types of electromagnetic forces would include applied forces. So an applied force is just something as simple as this. I could be pushing this calculator in this direction right over here. I'm applying a force to push and move this calculator in a particular direction. I could push down on the table. I would be applying a force downwards towards the table right over here. That's an applied force under the category of electromagnetic. It could be tension. So if you have a string tug of war, so on the first page of these notes right over here, when you see them pulling, there's tension in that rope with the donkey and the man, and that's going to be another force, a tensional force. At any given moment, this is a little bit interesting how the forces actually work within the rope here. They're going in both directions kind of continuously. It's very bizarre. But anyways, we'll get more into that later. Tensional forces, another example of electromagnetic force. Then you have your frictional forces. And these would be some of the different forces. And then frictional forces. So clearly you know what that one's all about. Even, again, calculator on the table, there's going to be a particular amount of friction. If I'm pushing upwards like this, there's going to be a frictional force that's going to be going in the opposite direction to the motion. And that's always true. If there is friction in a question, it always opposes motion. If the calculator is now traveling in this direction as I pull it, So it's coming down. That means that your frictional force is now going to be upwards in this example here. So as I pull it, your frictional force is going to be opposing motion. Frictional force this way. Your applied force is going to be downwards when I pull it. And then the reverse when I push it like this. As for relative strength here, a lot stronger. So if we just have this over here, relative strength is going to be 10 to the negative 2. As for its range, again, going to go with infinity. An infinite range here. Strong nuclear force. For the strong nuclear force, this is the force that holds the nucleus together. Very valuable within the different elements and the different atoms, right? So that way, all the pieces don't fall apart, and you're left with matter that's not cohesive. So if you didn't have matter that would actually kind of stick together, there would be no universe as we know it today. It just would cease to exist, or it would never have existed in the first place. So you have to have the correct value for your strong nuclear force. Yeah, if it was too strong, everything kind of would have, I think it's imploded on each other, and if not too weak, like the value for the strong nuclear force, objects, different elements would not have ever combined in the first place. So either way, it's a fine balance, the universe that we live in. So this one here is the strongest of all the forces. And so its relative strength is a value of 1. Strongest force with a value of 1. And it has a very tiny range. The range is actually less than 10 to the negative 15 meters. So very small. So like if you were to try to like even put a gap between your fingers, that would even be larger than whatever this is right over here. Less than times 10 to the negative 15. So the effect that the strong nuclear force has is only for a very small range right over here. You have to be incredibly close to actually have any of the effects that would go on with a strong nuclear force within there. So that would be within an atom, whatever that might look like. So if you have the nucleus, and then you have your protons that are somewhere around, and then your electrons that are kind of circling around that too. It's been a while since I've done any like particular drawings here. Not even sure if this would actually be a particular element. You get the idea, right? Different elements, different electrons, etc., etc. Maybe there's another valence shell over here with more electrons on the outside there. You can always correct me if I'm wrong on this one. So pick whatever element you want. Nuclear weak force, or the weak nuclear force. This is what causes radioactive decay. There's not much more I'm going to say about this one, other than the relative strength when comparing it to the rest of them is going to be 10 to the negative 13. So we're looking at the ranges here. This one is by far the strongest, followed by electromagnetic force, then the weak nuclear, and then lastly the force of gravity, the weakest of them all by a long shot. And then as for your range for this one, it's going to be less than times 10 to the negative 18. So its range is even 1,000 times smaller than that of the nuclear force. So it really only affects an incredibly small area. Probably why it's considered to be the weak nuclear force. But again, you can always study up more on this if you want to for interest's sake. Maybe there is something that you're like, wow, I really want to learn a little bit more about the microscopic levels of elements and atoms and the quarks and even the smaller pieces beyond just the electron, proton, and neutron. But that is not going to be something that we're going to be looking at right now. So, on to diagrams. Diagrams are incredibly important with dynamics, to be able to draw them, to be able to label them, etc. Because again, dynamics is what causes the motion. And so to get a better picture of what causes it, we should draw a picture. Makes sense. Label the forces, determine the net force. That's going to be key, determining the net force. And so often we're going to be labeling that F net. And so if this doesn't look like nets, this is net. I'll just let you know. That's how I kind of write it out. Here is a box. There are 4 forces acting on this box. And so we're going to be labeling all of them here. And let's start with some of these. Fg is going to be your force of gravity. This is your force of gravity. And even if we look at this right now, if you were to add up the vectors, you could say, okay, these are going to cancel, the force of gravity and this force. And over here you have a force that's pulling or opposing this force, but there's a net force of 30 newtons to the right. So what we're going to have here, I'm going to just tell you, this is our force applied. There's somebody pulling this box to the right. So we'll even just say that. Someone is pulling. And because someone's pulling, here is our applied force. That's what we're going to call this right here, applied force. So we have an applied force. We have the force of gravity. We also have our normal force. So before, when I was pushing down on the table, I was having an applied force that was down, and then the normal force would be in the opposite direction. It would actually be pointing upwards. So normal force often kind of opposes particular forces. And with only, it's always equivalent to whatever the force is in the opposite direction there. So in this case, due to whatever the mass of this object is, there is a 30 Newton force downwards. So the normal force is going to be 30 newtons upwards. Now if we put another rectangular brick on top of here, now you'd have a force of gravity potentially of 60 newtons. And then you would have your force normal being 60 newtons in the opposite direction. So if you double your force gravity, then your normal force is just going to oppose whatever your force gravity is. And that's the way it works. The only time that you wouldn't see this is, imagine I was to stack up this table with a bunch of weights. And so now there's the force of gravity. Whatever the mass of all the weights are, multiplied by gravity or acceleration of gravity, which is 9.8, you're going to get the force of gravity downwards. Now, the normal force will push back up against the table there. But if all of a sudden you put too much mass onto the table wouldn't be able to hold it. It would break. And then you're not going to be having the same normal force, obviously, at that point on the table, because the table would cease to be a table anymore. It would just be a broken table. Lastly, we have force of friction over here. So FF, force of friction. So in this example here, we have our force friction, force gravity, force applied, force normal. Force applied is it could push if we set up the question that way. Force of friction opposes motion. So we see that we're actually going to be moving in this direction, and we'll explain more as to why that is later. But it should also kind of make sense. So if there's only 20 newtons of friction and we apply a force of 50 newtons, there is going to be more force to the right than there is to the left. And so objects at rest will tend to stay at rest, but if you're going to be applying some type of force to this object, it's going to begin to move towards the right. And these two forces in the y direction will cancel. All right. Draw a free body diagram. So these are sometimes labeled as FBD for short, free body diagram. And again, very, very useful in dynamics. If we're trying to explain how motion works, we want to be able to get a nice picture of it to be able to see what that is. And part of a free body diagram is labeling all the acting forces and then determining the net force of each of these values that are given. So let's take a look. We have a fridge that's being pushed along a frictionless ground. How amazing is that? By two really weak men. One pushing with a force of 4 newtons to the east, while the other only 2 newtons to the east. Draw a free body diagram of this, labeling all acting forces, and determine the net force. So first of all, I apologize. My drawing skills are horrible. So yes, you can make fun of me all you want. Luckily, I'm not being graded on how poorly I can draw. So we got our handles over here for our fridge, freezer on the top, I guess. There's guy number 1, guy number 2. Again, this could take a while. I don't know where this guy is going to be. All right. So he's got really long arms here. There you go. Really long arms and short stubby legs. And both of them are pushing in this direction. Daddy long legs. Or daddy long arms. Daddy long arms is only pushing with 2 newtons of force, while the other one is going to be pushing with 4 newtons of force. So with twice as much there. It might be better to just to label this on this other side here, which is what we can do actually. So let's do that. From time to time, you will see where almost the arrows come from the middle, or just even on the outside of the box too. So it might be best here to have the 2 Newton one right here, and then the 4 Newton one right over here. One thing I try to do is represent them based on their magnitude. So if this one's twice the size of this one, I'm trying to make it twice the length. So again, I can visually see that this one has more force than this one just based on the drawing alone. Obviously the number does help out with that as well. We're not done with all of our forces. We've only done the applied force, right? Here's our applied force. There is no force opposing motion because we did say it is frictionless. And that does beg the question, well, can these guys actually push in this direction if it's frictionless? How would they be, would they just be sliding out? Let's imagine that there's a nice little plate over here that they're standing on that is full of friction. So a nice little mat or carpet right over here. The rest of this is a frictionless surface. There you go. So voila, off the refrigerator goes to the right after they begin pushing it. We have 2 other forces. We're going to have our normal force right over here. And then we have our force gravity. And so whatever length of this is, that's going to be the same as this one here. So remember, force normal is usually equal to your force gravity in certain cases. Please be aware that this is not always going to be true, and we will be looking at examples where a normal force does not equal your force gravity. So it usually can, but there are exceptions to that rule. So please think it through. Don't always think that force gravity is equal to your force normal. All right, we've labeled all of our forces, and then lastly, we want to say, well, what is our net force? Well, our net force is just the 2 forces that we have, our first applied force and then our second applied force. Oops, FA2. And 2 and 4, 2 plus 4. So our F net is going to be 6 newtons, and then we could draw a little arrow to the right. Forces do have our vector, and so we do need to have a direction when we give our answer. So we have units, we have a direction for the force. Something like this, that's fine. Number 2, a car slowing down as it approaches a stop sign. The car has a mass of 1,600 kilograms and the force of friction is 1,200 newtons. All right, this is going to probably be even worse. Okay. Yikes. Here we go. Okay. Wow, this thing, I don't know. Maybe this is This is the trunk of this ugly car over here. I don't know. This is beyond horrible. Okay, let's try this out here. Car is slowing down as it approaches a stop sign. So let's imagine that the motion, this is the front of the car right over here. This is the back of the car. All right. And we're going to have some opposed motion. So if it is going in this direction, we're going to have our force of friction over here being 1200 newtons. Again, we are going to have our force of gravity down over here, and whatever that is going to be also opposite your force normal in the other direction. Your force normal and your force gravity are going to cancel, and these are the only forces right now. There's no applied force because it says the car is slowing down, so we're assuming that they're just braking, that they're not actually accelerating, they're not pushing their foot onto the gas. And as such, the only force that is opposing this motion, it was traveling this direction. It still will be traveling this direction, but it's slowing down with a force of 1200 newtons in the opposite direction to the motion. And if we were to say, well, what is your net force is? Well, that's only going to be whatever your force of friction is, because these two cancel out in the y direction, leaving only this extra value right over there. So if our F net is equal to our force friction, and our force friction is 1200, then our F net is also 1200 newtons, and we look at our direction off to the right in this example here. For number 3, we have a 90 kilogram skydiver falling at terminal velocity. So there are certain examples where we will consider air resistance. This would be one of them. At a certain point, the force of gravity is going to be equal to the opposing force, your air resistance force, like the force due to air resistance. And so we can consider that to be a type of frictional force, right? So that's the way that we will label this thing. So we have some guy right over here, and whatever else. Falling, hands in the air, chute is somewhere on their back over here. They haven't opened it up clearly because they're at a terminal velocity. And what you're going to have is a force of gravity downwards. And in this particular case, your force of gravity and this upwards force here, your frictional force, due to air resistance, is going to be equivalent. So if you were to add these two together, and if you were to represent that in a formula, it would kind of look like this. You'd say, well, what's happening here? You have your force of gravity down, you have your force of friction up. But if you were to subtract the two from each other, because they are going in opposite directions over here, you are going to have a value of 0 newtons. So our F net is 0 newtons. And if you have 0, we're not going to need to state which direction that is. And number 4, a person jumping the moment before they leave the ground and the moment they leave the ground. So we have two situations here. The moment before they leave the ground, so we have the ground right over here, and off they are. So what are they doing here? Imagine that they are leaning back here. So they're bending their legs, and off their arms go like this, behind them, Naruto style, and they are going to be pushing upwards. So we have our force of gravity, whatever the mass of this individual is, times gravity. We're going to have our force normal, which is going to be in the opposite direction over here. And we also have our force applied. So we have our force applied over here. So these are different forces as they go. This one here, we don't have any values, so we're not going to be looking at saying, well, what is the total net force in this situation here? But if you do take a look at this, your net force is kind of going in the upwards direction, so this individual will be traveling upwards due to the fact that your applied force is going to be larger than your force gravity, and so you are going to be moving in the upwards direction there. And if we look at round 2, the ground is now shifted. There was an earthquake. And so now this individual is somehow twisting. Did a 180 because they were facing this way before. Now they're facing over here. Not sure how that happened. And again, their arms are behind their back, but they're in the air. So what's happening with this individual now? There's no force normal. They're not touching against the ground. There is just going to be a force gravity. And there's no other forces. There's no applied force at this point either. They use their applied force when they push off the ground. After they're off the ground here, the only force that's being applied to this individual is the force of gravity pulling this individual back down to Earth. And so, yes, at some point, the individual will get to the height, the apex of their jump, and then come careening back down to Earth at the whatever speed they came. That's what, or left, that's what they'll come at. Again, if there was no air resistance. So these are the two different situations. So only force of gravity, or in this situation here, you have the force of gravity, you have the force normal, and then you also have your force applied in addition to that. And again, we'll talk more about the interaction between these three later. Force normal, force applied, force gravity in a situation like this as it comes about. So before I leave you, I really want you to get a couple practice questions in. And so we want to jump into the next little piece of the notes right away. And there are three laws that Newton came up with. And I guess maybe he was the one to first look at that, but it became law because we studied it enough, no longer a theory. It's actually like this is the way things work. Law 1, an object in motion tends to stay in motion. And an object at rest tends to stay at rest. So that makes sense. If I was to leave this calculator right over here, it's going to stay right there unless some force comes along and interacts with it, like my hand, and then pushes it away. So an object is going to stay at rest. Well, it tends to stay at rest, right? Those that are at rest will tend to stay at rest. Those in motion will tend to stay in motion. And again, there can be opposing forces, but that is the key right there. These two pieces for law 1. Law 2 is this. This is what we're going to be using the majority of the time, where you're going to say our total force or our net force is equal to mass times acceleration. So if I was to take the mass of this calculator right over here and then figure out how fast did it accelerate off of the screen, we could then calculate, well, how much force did I use in order to apply that acceleration with this little tiny mass of this calculator here. If I applied more force, it's going to accelerate faster, and there will be a larger value of A acceleration. If I go with a little low amount of force, you're going to have a small net force, and you will also have a small amount of acceleration. So there's a linear relationship going on here. And thirdly, third law, every action has an equal and opposite reaction. So we have already begun to look at this with the force normal versus force of gravity. And so that's one concept within the third law. So let's actually just dive in and do a couple examples here. And I hope to not have to draw too much more, but here we go. A 95 kilogram cyclist is riding an 8 kilogram bicycle and applying a net force of 55 newtons east. What is their acceleration? So a couple things. If I skipped over it, I'm sorry. Units for force are in newtons. So if you want to write that down somewhere, you can. I thought that was something that was covered in a lower grade, but if not, then just so you know. Units of force are in newtons. We did talk about this one of the first days of school, I believe, too. Newtons N. And you could really figure out, well, what in fact is a Newton? Well, if force is equal to mass times acceleration, right over here, and this is a Newton, well, Newtons would also be kilograms times meters per second squared. So that is what a Newton is. You would say that 1 Newton is the same thing as kilograms times meters all per second squared. And all this is literally just multiplying mass, and mass is always in kilograms, and acceleration is always meters per second squared. So we're just combining those together, and voila, 1 Newton is all of this right over here. Just a nice simple way of minimizing the amount of units that we actually have. So instead of writing this every time, we just write N, representing a Newton. It makes it a lot easier then. Anyways, we got a cyclist moving towards the east, a total net force of 55, and we're being asked what is their acceleration. Well, we have a net force, we have mass, and so if we look at this formula up above here, force, mass, we can use this formula to figure out what is the acceleration. But first, we're kind of jumping ahead just a little bit. Let's see here. Ooh. Okay. Where is this going here? We need some handlebars. This is going to be really, really rough. I don't know. Normally I just draw little blocks. A blob represents this individual here. I can't draw a bicycle. I don't know how many of you guys can draw bicycles. We'll just like put circle, circle, attach it like that. This guy's sitting on nothing really. We'll call that a day there. Wow. Anyways. Okay, what do we got? We got our applied force off to the east over here. We got our frictional force opposing motion. It didn't say necessarily that we had friction in this question. Like normally it's gonna tell you, so let's just say there was a frictional force. So there is a frictional force. Next, we have the force of gravity pulling downwards, and we have the normal force opposing it. Similar to that, the law that we noticed before. Every action has an equal and opposite reaction. Let us go ahead and label what we all have here. So we have our normal force equaling our force gravity. So that cancels those two forces out. They're equal and opposite. One is up, one is down. They are equivalent to each other in magnitude. Now if we look at what are our net forces, because that's what we're trying to figure out here. So what are your net forces? You look at these two forces, it's your force applied. So this is the greater of these two values here. So it's going to be our force applied, positive to the right, and then minus, since this is going the opposite direction, we are going to have a negative or subtract our force of friction. So it's going to be this minus this is going to give you your total net force. And so if we were to even do that visually speaking, it would be something kind of like this. That's going to be what your F net is going to look like approximately. F net is this. F net is also mass times acceleration. So let's go ahead and extend that as well. So if F net is mass times acceleration, and this is also F net, then we can say, well, these are equal to this due to the transitive properties. At this point here, we could then plug in what values that we do know to solve for that which we don't know. And to be real here, this is useful just for like visually seeing what's happening here. But because we don't actually even have any applied force or any frictional force, we will just even collapse this for now. So this is again useful. Some of the time you will have to expand your F net formula to include what is actually happening, what are the forces involved that will add up to your F net. But in this particular question here, we don't have an applied force, we don't have our force, frictional force given to us value-wise, and so we'll just be using F net is equal to mass times acceleration. And now we can isolate our variable A. We're going to divide by m on both sides. And what we're left with is your total net force divided by mass is equal to your acceleration. Our total net force is 55 newtons. As for your mass, this mass is man plus bicycle. So mass is going to be your total mass. Is 95 plus 8. Put that in brackets. So even if we looked at this 55 over just over 100, you should get an answer just larger than 0.5. And let's end up putting this at 8.0 so that we can then say that our acceleration is 0.53 meters per second squared, and it's moving towards the east. accelerating towards the east, actually. Well, both. We have our units, we have our direction, and we have our value. So it's very slow. He's very slowly accelerating. It's due to the fact that his total force is not very large right over here. Not very large. If he had a larger net force, then you would have a large acceleration. Maybe it's due to the fact that his force of friction is quite large, right? He could maybe be applying a large applied friction. Perhaps he was riding against wind. And so now his force friction due to the ground as well as air is going to be quite large, and he's not actually moving very quickly and not accelerating very much. 105 kilogram hockey player, and if you want to just get context, if you want to say, well, how large is 105, or even just like mass wise in pounds, you would go 105 multiplied by 2.2, and you're going to get a value of 231. So this hockey player is 231 pounds. So that's a conversion rate to go from kilograms to pounds. You multiply by 2.2. So in the last question there, when you had the 95 kilogram cyclist, that individual was 209 pounds. So just for reference point. And that bicycle seems like it's pretty heavy at 18 pounds. If you're getting a well-made, expensive bike, I bet you could probably get something for like 10 pounds. I might be wrong. So there you go. The 200 plus pounder, the 105 kilogram hockey player, was skating at 14 meters per second. And so again, if we want to have context just for a moment, it's useful to know. Similar to 50 kilometers an hour. So going very, very quickly. I just multiplied by 3.6. Is now only 3.8 meters away from the boards. So was traveling at 14 meters per second. If he can apply 2,500 newtons of stopping force, will he stop in time? So let's take a look. What are some of the values that we have? So we're not going to do TAD-VV per se, but we can still kind of gather the information. We have a mass of 105 kilograms. We have an initial velocity of 14 meters per second. And again, it's in whatever direction we're kind of drawing here. So let's draw to the right here. If we have the individual riding along on his skates here, big old skates, and he's pushing on his leg, I guess, something like that. This only gets worse each time. So you have your initial velocity of 14 meters per second. You have the boards over here, and this distance is maybe accurate. Not that accurate, though. Based on the height of this individual, if he's a 200 pounder, probably over 6 feet tall. So that's close to 1.8 meters. Anyways, 3.5 meters here. We have the boards over there. We have a couple other forces here. We're going to have the force of gravity. We're going to have the normal force. And then we have the stopping force. And so that's going to be in the opposite direction. So we have our applied force, which is going to be stopping this individual right over here. Sorry, I got distracted with drawing this picture. We can continue labeling the rest of the things that we do know. But here are the forces involved. So this is not a force, but this is just an idea of like this individual is going to the right at 14 meters per second, or at least towards the boards. The forces are the applied force in the opposite direction, your normal force, and your force gravity. All right. So we're going to be saying, okay, the displacement is going to be potentially 3.8. So we'll be getting back to that. We have our net force at 2,500 newtons. And we want our final velocity. What's our final velocity going to look like? So if individual is stopping and we want it obviously to stop before the boards, then our final velocity, we're going to be target value is 0. So we'll have a final velocity of 0 hopefully. But again, we don't actually know all this information. What we do know is that he's applying 2,500 newtons of force. We do know that the initial velocity is 14. We do know that the distance between him and the boards, did I label that incorrectly? Sorry, this should be 3.8 over here, 3.8. I'm sure somebody was saying that on the video, and I couldn't hear you till now. So 3.8 meters right over there. What was I saying? Oh yes, we don't actually know if he's going to be at 0. Like that's obviously the target value here as he slows down. But the question is, will he actually stop in time? If he doesn't stop in time, he's going to still have a velocity at the end. If he does stop in time, well, then he will have a final velocity of 0 before he reaches the end then. So if we're going to be kind of going through this, we know a couple pieces of information. And so with a lot of these questions that we're going to be looking towards the formula F net equals mass times acceleration. In this question, we are told what our stopping force was, and our stopping force ends up being our net force because it's the only force that is opposing the motion. And we also know his mass. It was given in the question at 105 kilograms. So we could actually calculate acceleration. Acceleration is going to tell us, well, how quickly is this individual stopping? How quickly is this individual stopping? So we have our F net is equal to mass times acceleration. We're going to be solving for acceleration, so it's going to be F net over the mass. Something to keep in mind here too, let's jump back to this. This 2,500 newtons, if he's moving to the right, and the total forces are opposing it, this applied force here, there is something that we missed. And so be very, very careful. I need to be very, very careful too. So I can forget this from time to time, but it's actually going to be negative 2,500 newtons. You are applying this force to the left. The applied force is kind of the same thing as your net force in this situation here, because that's the only force that's opposing motion. These two forces in the y direction are canceling out. That means he's going to stay on the ice as time goes along, so that's a good thing. But it's a negative 2,500 because it's a kind of opposing motion. It's going to be in the opposite direction there. And even if you were to plug this in over for acceleration, mass is always going to have a positive value here. So in order to decelerate or to oppose motion, if the velocity is this way and you want to decelerate, it has to be in the opposite direction to your velocity. You're going to have a negative value for your F net and to have a final value that's negative for acceleration as well. All right, let us plug in our values here. So we're going to have negative 2,500 over our mass of 105. Our acceleration is going to be at negative 23.8 meters per second squared. And this is our intermediate step here. It seems that our significant figures, if we look all the way around here, are 2. So when we do intermediate steps, we like to have one extra additional significant figure until we express our final answer. So we're going to have 3 significant figures here. Once we have our acceleration, and there's a nice marriage between dynamics and kinematics. And so maybe it was best for us to do the TAD-VB because we now have our acceleration, we have our what we think is our displacement, final velocity, initial velocity, etc., etc. So there's going to be one of these values in which we're going to be like, okay, we don't actually know if that's true or not just yet. So let's take a look and say, okay, we want him to stop and have a final velocity of 0. So is he going to actually be able to do that in 3.8 meters? We should put kind of a question mark there for now because we really don't know. Will he stop in time? Do we really need time in this question? No, we do not. What we're going to be actually looking for is what is the actual displacement if we choose these following values. We're going to be choosing our final velocity, we will be choosing our initial velocity, and we will be choosing acceleration. So now you can take a moment to look on your formula sheet. Where is there acceleration, velocity, final, and velocity initial, where you're trying to solve for displacement. Because again, this is how much distance he has in order to stop, but is he actually going to stop there? So we could have solved this one of 2 ways. By making a guess as to what the displacement actually is, or we could then say, okay, the displacement actually is 3.8 meters. What will his velocity be at 3.8 meters? So there was actually 2 ways to solve this question. So we're going to be looking at it, well, we're going to say, yes, he does stop, but how long will it take him to actually stop? So maybe you pause the video, maybe not. If you came across this formula right over here, final velocity is equal to initial velocity squared, both of them squared, add 2 times acceleration times displacement. We are going to solve for displacement. We will subtract initial velocity squared and then divide by 2a on both sides. This gives us our equation that we can then plug in our values. So we have a final velocity of 0, an initial velocity of 14 squared, which is negative 196, all divided by negative 19.6 when you go ahead and plug in these values right over here. Oh, sorry, what am I doing? This is not 19.16, our acceleration. I'm so used to using gravity. Negative 23.8. There we go. So we have a negative value on top, we have a negative value on bottom. We're going to have a positive displacement. That makes sense. He was traveling in this direction and he's slowing down. And so our final displacement is actually going to be 4.1 meters. So if it takes him 4.1 meters to stop, but he only has 3.8 meters to stop in, will he stop in time? No. He will hit the boards. He's going to hit the boards. So like I said, there's 2 ways to solve this. One of the ways was to assume that your final velocity is 0 and then say, well, how long would it take to actually travel that? The other way is you could have assumed that, yes, what will his final velocity be at 3.8 meters? And so you could have tried it out that way too, where you would have been solving for your final velocity, plugging in 3.8. I don't seem to have any room to do that right around here. Let's see if I have a blank piece of paper somewhere. I'd like to try this out. We're ad-libbing right here. So what I'd be doing is using the exact same formula. This time I'd be solving for your final velocity. Plus or minus the square root of vi squared plus 2ad. In this case here, our initial velocity was the 14 plus 2 times negative 23.8 multiplied by the displacement of 3.8 and then square root of all of that. All right, we have 196 multiplied by 2 times negative 23.8 multiplied by 3.8. We're going to get a value of 15. Take the square root of that. And we're going to get 3.9 meters per second. So at 3.8 meters, literally when he hits the boards, he will be traveling 3.9 meters per second. So clearly has not stopped. So that's why there was 2 different ways you could have gone ahead and solved that problem. So you could have solved it saying, I don't know what my displacement is, like how, if he actually stops, how long will it take him to stop? Or you could say, well, he only has 3.8 meters to stop. What's his final velocity? Will his final velocity be 0? If not, well, then we know that he didn't stop in time. So often there are multiple ways to solve the problem. It's not always going to be cut and dry. Sorry, this is a little bit of a longer video. There's a lot to cover. Let's see if we can just power through these last 2 here. The tennis. There was just the French Open where Nadal actually won it against Djokovic. It was quite a treat to watch. He won his 20th Grand Slam title. Number 3, tennis player, maybe we'll call him Nadal, serves the 58.5 gram ball so that it went 0 to 73 meters per second in 0.003 seconds. So it accelerated at an incredibly large amount, which should make sense, right? It doesn't hit the racket for very long, and all of a sudden now it's traveling incredibly fast. What is the total net force acting on the ball? And we are going to just ignore gravity for now. There's a couple of things that we're going to need to take note of. First of all, we have grams and we're going to need kilograms. What are the kilograms? So there's 1,000 grams in a kilogram. So if we were to label our mass over here, our mass is going to be 0.0585 kilograms. You're moving it 3 decimal places to the left. We have a couple other pieces of information that we do know. So this time I'm going to go back to my organizational roots right over here, just to start plugging information that I know in an organized fashion. So 0.003 seconds. What's the F net? So don't know our acceleration just yet. Do we know our displacement? No. Do we know our initial velocity? Yes, 0. And then our final is 73. So even if we take a look at these pieces of information right here, we're not going to need displacement. Like, how's that going to help us? We do know that our Fnet formula looks like this. Fnet is equal to mass times acceleration. We have the mass. We probably could calculate acceleration, and then that would give us our Fnet. So as long as we have acceleration, we could have our total net force. Well, if we look here, we have 3 pieces of information right now. We have our final velocity, our initial velocity, and our time. So recognizing that we have 3 pieces of information looking to solve for acceleration, look for the formula that does not include displacement. If you can find the formula that does not include displacement, that would be the one we would use to find acceleration. So look to your formula sheet. What you might find is acceleration is the change in velocity over time. And I will just skip to this next line right here. Change in velocity is final velocity minus initial velocity over time. And your final velocity over your initial velocity, I want to put it on this line actually. Final velocity is 73. Initial velocity is 0 over the change in time, 0.003. This is a very, very small amount. So when you divide by a number way less than 1, you're going to get a number way larger than 1 on the top in a case like this. Your acceleration will be 2,400. Let's see here, 3, whatever else. The rest, this one has like 4. No, only 2 actually. Let's call this 0, 0. All right, whatever. 24,333. So if we're going to go to 3, then we'll just round these down to 300 meters per second. We have acceleration, we have mass, we can find our Fnet. Just plug in the values now. Fnet is 0.0585 multiplied by our acceleration of 24,300. .0585 multiplied by 24,300 is 1421. So we're just going to write this over here for 21.55. And if we're going to be rounding to, let's say, only 2 significant figures in total, you're going to be looking at 1,400. 1,400 newtons. And in this case, depending how it goes here, like we don't really know which way did the tennis player serve it. So it didn't say east, west, north, or south. So in this case, we'll just have to leave it like this because it doesn't specify in what direction. So yes, as much as you can, you'll express your direction for your forces. But if there's a question where like there's literally nothing given here, then we'll just leave it as this right over there. All right, last question. A shipment receiver guy is pulling a 6.087 kilogram cargo trolley with a large pallet of material. He is pulling with a force of 175 newtons north. The force of friction on the cart is 151 newtons. What is the normal force acting on the pallet of material if the trolley is accelerating at a rate of 2.3 meters per second squared? So there's some guy pulling a trolley. So got an individual over here. And maybe the way I'm showing it now is he's just pulling it backwards. So he's moving in this direction over here. And so here's the string. And we got our wheels over here. And then we got like all these like little pallets that are stacked up over there. So maybe I should have drawn this a little bit further this way. I didn't really think of that before. Anyways, what do we have here? We have an applied force to the right of 175 newtons. We have the force of friction, the opposite direction. The force of friction of the cart is 151 newtons. So I would have liked to draw this on the left of this cart here, but I drew this too close to the edge. Then we have our normal force, and then we have our force of gravity going down like this. So these are the different pieces that that are actually happening here. And I think that's basically all the different forces here that we're looking at. We're asked for what's the normal force acting on the pallet of material. So here is the trolley. And we're saying, well, what's the normal force of the actual pallet? So all of this stuff right over here. All the stuff stacked on top of the trolley. So this box, and this box, whatever other boxes there are there. Those are the boxes that we're looking to say, well, what's the normal force on that? So there's a lot to this question right over here. So let's start by breaking it down. What do we know? We know that we have a mass, a total mass. So we're going to put a little t there for the total mass, because if we're going to look later on, we're going to have a trolley mass, and we're going to have like the rest of these pallets over here, and whatever that mass is. And we do need to know that there is a difference there, because when calculating the force normal, we're not going to be including this trolley, because the trolley doesn't have anything to do with like what force is being pushed down due to the pallets. It has nothing to do with the trolley. If we were saying what's the normal force on the wheels, well, then that would look a lot different, right? So, or even let's say this was like a track right over here, a trolley that had a track. Yeah, what's the normal force on the trolley in the opposite direction? Then it would be the mass of everything now. But because we're dealing with just the pallets, it's going to be just the mass of that. So for now, we've been just given this total mass, and we don't know what the mass of just this piece is right here. So we're going to actually have to find that if we're going to want to find what the normal force is, because normal force is equal to force of gravity. And one thing we haven't mentioned yet is that force of gravity is equal to mass times gravity. So our total mass is that value right there. We have our frictional force, our applied force. We have our acceleration being 2.3. Says it right over here, 2.3 kind of in this direction right over here. So if we have our total mass and our total acceleration, we can actually calculate what our F net is as well. All right. So let's go ahead and do that. What we're going to do first is write out our F net formula, though. Our F net formula. What's the total forces involved in here? That's where I like to often start when I'm drawing up my formulas. It's your applied force to the right minus the force of friction to the left. So it's your applied force minus your force of friction. And what that's going to look like is the following. And I might have read this wrong here. Shipment receiver guy is pulling 6.0 kilograms of cargo, the cargo trolley with a large pallet of material. Oh, sorry, this is the cargo trolley. This is the trolley here. If I could only read. So no longer total, we'll call this trolley. Sorry about that. This is the trolley. So it's not actually the total. We're still going to have to find the actual total, I guess. We want to find the total if we need to find the F net. So this is just for the trolley, sorry. So just for that bottom part right there, that's this value here. It would pay to read. It's a little bit late too, so I say good morning, but it's almost midnight. Okay. Our F net, our applied force is 175 minus 151. That is going to be your total net force. That is 24 newtons off to the right. Now that we have our total net force based on our applied force and our frictional force, we can now say, well, what is the total forces involved over here? So to find the total mass, we will now use the F net equals mass times acceleration and rearrange this by dividing both sides by acceleration. And we get mass is F net over A. Our F net was 24. Our acceleration is 2.3, so we're going to get a value of just more than 10. 10.435. We have our total mass over here, and we have the mass of the trolley right over here. So if we want to say what's the mass of the material or mass of the pallets, mass of pallets, well, if you have the total being the mass of the pallets plus the trolley, so if you have like the mass of the pallets plus the mass of the trolley equaling your total mass, then you can just rearrange that, because clearly if you add these two together you get your total. So what would it be just for the mass of the pallets? It's going to be your total minus your minus the trolley, right? So maybe I didn't need to draw that all out, but that's fine. Subtract this value over here, you're going to get 4.348 kilograms. And the last thing is this. We had said that whatever the mass of the pallets is, that's going to be part of this force times gravity. Well, force times gravity is equal to mass times gravity. So the last section here, force of gravity. And please be aware that we will be doing more of these types of questions in the future too. So your force of gravity of the pallet is equal to the mass of the pallet multiplied by gravity. And this whole thing is also just equal to your Fn, your normal force. So we just plug in our values for this, and we will have what our Fn is equal to, because the Fn equals the force times gravity. So from here on out, because this is equal to this, which is equal to this, I'll just say Fn equals this as well. Mass of the pallet is 4.348. Gravity is 9.8. Multiply these out, and our normal force is going to be 43 newtons upwards. Sorry, I was missing some of those values there. Don't always look at my camera. You can take a quick look at that. But yeah, there's a lot to this question right over here. So some of it is drawing it out, writing out some of the piece of information you know. This is a must, drawing out what is your F net to be force applied minus force friction. You calculate this out, also knowing that F net is always equal to mass times acceleration. So this was the one piece that I messed up on, so sorry about that. Make sure to read the question, maybe even reread it. So maybe don't do work at midnight either. So that's always a thing to be aware of as well. Although it might not be midnight. Just feels late. That is it. I've been rambling on for too long. Sorry about that. Have a great day. I hope that you learned something today, and we will cover whatever we didn't cover today tomorrow. And so good luck. Have fun.